I bought an apple so it could work. Oh, guys, webcam's on.
Oh, hi guys.
The camera's there, Nicole.
Hi guys.
Yeah.
Okay, let's start. Could you tell us a bit more about yourselves?
Well, for starters, we're all elements who are ions who are electrons and are d orbitals. This means that not every d group atom is a transition element, as they may form ions without d orbitals, like scandium and zinc, but we love them all the same as they stay with us. We're family. Whenever we feel the need to become more stable electronically, we just lose electrons, pretty much like everyone else in the periodic family. But we're very different. We don't just form one kind of ion, we can form many. For me, I could be Fe plus 1, Fe plus 2, Fe plus 3, Fe plus 4, Fe plus 5, and even Fe plus 6. That explains why we're so fun and unpredictable. So let's do a short introduction to some of the more important members of our family.
So tell me, why is it that we tend to see some of your ions more than others?
Well, some of our family members don't really come out as much as others really. They aren't very stable, you see. That's why Fe2 plus doesn't come out for a long time. He gets unstable too fast and has to lose another electron. I, on the other hand, can last much longer.
So what's so different about all of you? I mean, I met calcium the other day. Well, one of those ordinary S-blocks elements, if you will.
We're all very different. For one, let's look at our atomic and ionic radiuses and see how they help us to understand the trends which are present among us. As we go across the period in the D group, we see a slight decrease in ionic radius. This is because across the period, nuclear charge increases, but additional electrons enter the inner 3D subshell. These inner 3D subshell with electrons provides a greater and more effective shield around the nucleus, which causes the influence of the additional protons to be lessened. As for melting point, all the transition elements also have melting points of over 1000 degrees Celsius, much higher in contrast to those of S-block elements such as calcium. This is due to our strong metallic bonding, because both our 3D and 4S shells are available for delocalization. This also makes us very good conductors of electricity, as more electrons can flow across to carry an electric current.
We also have very strong metals, very tight and compact. This means we're much denser than objects like calcium. Yeah, we're very dense and we like it. Iron, what's 2 plus 2? 5!
It's all about how your electrons are arranged, which causes you guys to have such traits. But how about ionization energy, where we want to remove 1 mole of electrons from 1 mole of any of you?
Our ionization energies are mainly the same, with a slight increase as we move across the period towards copper. This is because most of our outer 4s subshells have either 1 or 2 electrons. In cases where there are more than 1 electron in the 4s subshell, the energy required is usually also the same, as that element would usually have a well-filled 3D subshell, which increases the amount of energy required to take the electron away, and vice versa.
Oh, and I heard that you are all very famous in your work in catalysts.
Oh yes, it's been part of the family trade for many years. You see, in industrial reactions used to provide certain materials, a catalyst is used to reduce the activation energy of such reactions, providing an alternative energy pathway. Because of our numerous oxidation states in which we lose electrons to form stable and even more stable ions, we can be used to release electrons to form such alternative energy pathways by allowing the reactants to react differently while not changing the outcome. We essentially give off electrons which help in the process, but are spectator ions too and don't bond to any of the main reactants. Or, given that we also have vacant spaces in our subshells, we can also act as avenues by which electrons can be taken away from the main reactants. Ultimately, this accomplishes the same thing.
Well, that's great work. Oh, and one more thing I had to ask you about. What's with the awesome colors you guys come in?
Oh yes, we're very proud of that. We're colored due to a special thing called DD transition. In short, the ability to produce a color in us is based on the presence of our half-filled 3D subshells. Any element with either a vacant or fully filled 3D subshell will not have any color. In short, the interaction of electrons in the 3D orbital under certain circumstances propels the electrons into a higher energy level. In short, the interaction of electrons in the 3D orbital under certain circumstances propels the electrons into a higher energy level. This produces a wavelength of light which falls into the visible region of the electromagnetic spectrum. Therefore, in my case, my wavelength falls within 600 to 650 Hz, allowing me to absorb orange light and be beautifully blue.